Hello everyone. So we are back again with another class. Now let me quickly introduce for those of you who are new to the stream. So we have these classes every day. These classes are on DS algos, right? So data structures and algorithms. Some problems that have been asked in a lot of companies, right? How do you actually approach a problem and how do you solve complex problems? Right? These classes happen every day at the same time, 6:30 p.m. to 7:30 p.m. Indian Standard Time. And once this class is over, there will be an assignment that you will be able to attempt. That assignment will have a set of questions, so that questions will help you apply whatever you have learned in the class. Right. So the link for that will be in the video description. All right. So today's topic is once again binary search. So we have been continuing. We have been studying binary search in the past two lectures. Right. So if you have not watched those past two lectures, please go and watch them. They will be on the Scalar YouTube channel, Scalar Academy channel on YouTube. So let us continue with some more advanced problems on binary search today. All right. Let me just share my screen. I hope that everyone can see the screen. All right. So let us start with a question that you might have seen earlier. Right. It is a pretty famous question. And you might have seen this in the arrays, 2D arrays class that we already had, right? But this question is relevant to binary search, so let us quickly see it here once again. Question goes something like this. You have been given a matrix. I mean, this is not that matrix movie thing. This is a matrix. It's a 2D array, right? Now, this matrix can have a certain size. Let us say that the size is n cross m, right? Now, this one property in this matrix that each row and each column is sorted, right? So let us quickly take an example of what such one such matrix would look like. So suppose we have 10 over here, 20, 30, 40, 50, right? All right. What other numbers can we choose? So let us suppose that we have 15, 25 perhaps, 35, 45, 55. Something else, maybe 27, right? 29, 29, 37, let us say 48, and let us say 60, right? So let us just add quickly one more row. So suppose this is 32, and suppose this is 40, suppose this is 51, suppose this is 60, and suppose this is also 60, right? So we see that in this matrix, every row individually is sorted, right? Every row individually is sorted, and so is every column. So is every column, right? Cool. All right. Now, what is the size of this particular matrix? Well, over here we have 4 rows, so n equals to 4, and m equals to, we have 5 columns, so m equals to 5. So this is a 4 cross 5 matrix, right? Now, we have been given an integer. We have also been given an integer k. Right? So k stands for key. We have been given a key, and we have to search this key. We have to search this key within the matrix, and we have to return, we have to basically tell whether the key exists or not. Key exists or not. Fair enough? Yes? All right. So Rahul has a question over here. Rahul, I guess, is talking about the assignments that were given in the last class. Rahul says that 5 questions in 24 hours is kind of aggressive. Right? So Rahul, you do not have to attempt those questions in 24 hours. Right? So unlike when you are enrolled in Scalar Academy, you will have a lot of guidance. You will have mentors. You will have TAs that will be helping you while you're working through the assignments. Right? We will have remedial classes a lot. When we are on YouTube, we just want to give you as many assignments as we can so that you can practice on your own time. Right? So it could be the case that yesterday, after taking the class, you were able to solve 2 of the problems. Now, maybe 5 days later or 10 days later, you want to come back and try it again. Right? So we just want to make sure that you have some new problems that you can still attempt. All right? So do not worry about the time constraint. This assignment is not timed. Right? So feel free to take this assignment whenever you want, how many times you want. So it doesn't really matter. Okay? Just the assignment is just to make sure that you can practice a lot. Perfect. So yes, Shazia is saying that this question has been done in the previous class. So we are going to very quickly move through this question, all right? But this is kind of important for binary search as well. So as you guys already know that this is binary search question. So let us just quickly recap this, all right? Perfect. So this is the question. You have been given a matrix of size n cross n. Each row and each column is individually sorted. Given a key, we have to find whether this key exists in this matrix or not. Yes. Perfect. So what approach do we have? Well, one of the brute force approaches. So whenever we have a new problem, we try to come up with a brute force approach. Brute force approach, right? In a brute force approach, we will not be using any extra information that we are given, right? So what will be the brute force approach? We simply try to linearly, so linear search. If we search through the entire matrix in a linear manner, then how much time is it going to take? What will be the time complexity? Well, how many elements are there? There are total n cross m elements. We are doing a linear search, so it will be the complexity, the amount of time it will take us for linear search will be order of n cross m. All right, but we can optimize, right? We know that each row and each column is individually sorted. Interesting. Well, let us just worry about the rows for now. Let us just worry about the rows for now. So we know that because each row is sorted, we can binary search. Inside each row. Is that correct? So if we binary search, let us call this binary search 1. If we binary search inside each row, then how much time is it going to take us for every row? Well, there are m elements. In a row, right? There are n rows and there are m columns. So every row has m different elements. So if we want to binary search among m elements, it will take us log of m time. Right? This is for one row. Now we have to do this for all the rows. How many rows are there? N different rows. So it will take us order of n times log m time. Yes, do you guys agree? On the other hand, if we basically, so this is on the rows. If we binary search number 2 on the columns, right? Then it will be very simple. So it will be m times log of n, because now we are searching within each row, right? We are searching within each column. And how many elements are there in a column? Well, equal to the number of rows. So we can search through a column in log n time, and we have m columns to search through, right? So if we search through just the rows, we will get this complexity. If we search through just the columns, we will get this complexity. The question is, can we do better, right? Now, this might not be obvious from the question itself. We have already tried binary searches, right? But binary search is not always about this binary property. Right? So just because you are saying binary, that does not mean you always have to split the array into half, right? That is originally what binary search means. But binary search has a more important underlying concept. And the concept, as we discussed in the previous classes, is what? The concept is that given a search space, when you make a guess, you are able to eliminate a large part of that search space, right? So every guess allows you to eliminate a large chunk of the search space. Perfect. All right. So that's fair enough. So how can we basically do that? For this particular question? Well, we can observe. Let us suppose that we are looking at this particular element. Let us just pick any random element and let us say that we are looking at this particular element. Right. Then, if we determine that given our key, right? Let's say that we compare this key with 45. Suppose that the key is less than 45. Right? Suppose that we are looking for an element like 29. 29 is less than 45. Right? Then what can we know from here? This key was less than 45. So can this key be over here? Can this key be in this area? No, right? This key cannot be in this area. Why? Why can it not be in this area? In fact, this particular area, because this key is less than 45, and everything in this area, everything over here in this area is already greater than 45, right? So the key cannot be over here. Similarly, so I can reduce my search space, right? I can reduce my search space by a large chunk. This might be a large chunk. Right? Now there's one more property that we get. If we move in a particular order, right? Suppose that we are starting from the top right, then we can also eliminate some more rows or some more columns. Right? So we will see that we will be able to eliminate this top row as well. Right? So over here, there's nothing binary over here. Right? We are not really splitting the search space into half. However, what we are able to do is we are still able to eliminate a large chunk of the search space with every guess. Yes, so Dev has a nice name over here. Dev is saying that we can call this staircase search, right? And yes, Tushar also points out one thing. So Tushar says that this has already been discussed in a previous class. So yes, it has been discussed in the array class. However, it is important enough to bring up again in the binary search class, right? Just to stress the point that binary search is not just always about binary search, right? You can still do sort of a binary search on even though you're not splitting the data into half, right? So very quickly, how can we do the search now? Suppose that we start from the top right. So once again, let us assume that the key we are looking for is 29. We are looking for the value 29, and 29 happens to be over here, right? So we better reach this point. But for now, we don't know where the key is, so let us start from the top right. And we will compare 29 with 50. 29 happens to be less than 50. Since 29 is less than 50, what can I eliminate? What part of my matrix can I eliminate? So where can 29 definitely not lie because of this comparison that I have just made? I know that in this particular column is sorted, right? So over here, in all this column, every element is greater than 50, is greater than equal to 50. And we already know that 29 is less than 50. So my key cannot be in this column, right? My key cannot be in this column. So I can eliminate this column. Do you agree? Yes. All right. Once I have eliminated the column, now I have a different matrix, right? I have a different matrix. The matrix exists only up till this column, right? So what is the top right part now? What is the top right part of the matrix? It is this particular cell. All right. Let us compare once again. So we know that 29 is again less than 40. So once again, by the same argument, since this column is sorted, then 29 cannot be in any of these elements because we know that 29 is less than 40. So let us very quickly eliminate this column as well. Perfect. Let us move on to the next top right element. So this is 30. 29 is still less than 30. By the same argument, we will be able to eliminate this particular column. Does that make sense? Yes. Let us continue. So now the top right element is 20. Right? 29 versus 20. What is it? So 29 is greater than 20. Well, now a different argument appears. Let us look at the different argument. So we know that 29 is greater than 20. Right? So if we look at this particular column, if you look at this particular row, we know that everything to the left of 20, everything to the left of 20 over here, in that same row, right? That has to be less than 20. Everything to the left of 20 has to be less than 20 because the row is sorted. So 29 cannot be over here. So what we can now do is we can eliminate this particular row. And notice that these columns have already been eliminated. Right? Excuse me. We move on to the next top right element. So 25 is the next top right element. We compare once again. 29 happens to be greater than 25. So by the same argument, we can eliminate this row. Then we move to the next top right element, which is 29. And now we can return yes, we have found 29 and 29 exists in our matrix. Is that clear? Yes. So we are not doing binary search. We are kind of doing a staircase search, right? We are zigzagging around. So in this particular case, we moved along this path. There's nothing binary about this, but this is still an example of binary search. Is that clear? Cool. Now, very quickly, what will be the time complexity? Time complexity of this approach. So we have already seen that linear search takes this much time. Binary search will take either n log n time or m log n time. What about this particular approach? Well, for this approach, we have to go from the top right corner, in the worst case, to the bottom left corner. Right? From the top right corner to the bottom left corner. And the path does not matter. The path does not really matter, because in both the cases, we will be covering n different rows and m different columns. Right? So our total path length is equal to n plus m, irrespective of what paths we take. Right? Either we go this way, or we directly go over here, or we maybe take this weird way. Right? All these cases have the same path length of n cross m, m plus n. So the time complexity will be order of n plus m. Is that clear? So this was a repeated question, but this was still very simple and very relevant to binary search. Let us move on now. So we very quickly saw this question. Let us move on to the next question. So Animesh over here says, can we rewrite this? So Animesh says that, okay, perhaps we can also rewrite this as order of max of n comma m. And that is true. That is true. So as we saw in the very first class on time complexity analysis, we saw that we can rewrite this part as max of n comma m, right? Because asymptotically, these complexities will turn out to be the same. They are related by a constant factor of each other. All right? Perfect. Moving on, let us see a more challenging question. So this question is very famously called aggressive curves. Aggressive curves. I think this question was originally from the platform Spoj, right? And this question is very, very common. I mean, this question happens to be one of the favorites for all the companies. So this question has been asked numerous times at Google. This question is still asked very frequently at places like DirectTime and Amazon. And this is a very, very nice question. Right? The special thing about this question, as you will see, is that it has a very nice solution using dynamic programming as well. But it can also be solved using binary search. Right? So a lot of the times when a student goes to an interview, they are expecting a difficult interview question, right? A lot of the students are afraid of dynamic programming, even though dynamic programming is pretty easy, right? So whenever they see this question, the natural approach, the natural idea that comes to their mind is, okay, I can try dynamic programming on this particular question. I mean, of course, dynamic programming solves this question, but binary search solves this in a faster manner. Okay, so let us quickly see the question. The question goes something like this: that you have n different stalls. You have n different stalls, right? And the stalls, so let us say n is greater than 2. You have n different stalls. So you have more than 2 stalls. And you have C cows, right? Once again, C is going to be greater than 2. There's one constraint over here, that C is less than or equal to n. All right? We have n different stalls and we have C different cows. Now, you have been given the location of these stalls. The location of these stalls has been given to you. So let us say that we have 4 stalls, right? N equals to 4. And the location of these stalls are 1, 2, 5, and 8. All right? Or let us make this n equals to 5. Let us just add one more. And 1, 2, 5, 7, and 8. What that means is that the first stall, the 0th stall, is at location 1. The first stall is at location 2. The second stall is at location 5. Third stall at location 7, and fourth stall at location 8. Right? So you can try to imagine this, that this is one stall, this is the other stall, this is the third stall, this is the fourth stall, and this is the 5th stall. And if this is at 0 meters, then perhaps this stall is at 2 meters, then this stall is at 5 meters. Right? This stall happens to be at 7 meters, and this stall happens to be at 8 meters. So they are unevenly spaced. Right? These stalls are unevenly spaced. Now we also have C cows. Right? Suppose for this example, we have we have 3 cows. Right? C equals to 3. So now our task is to place these cows. Our task is to place these cows into the stalls. And one cow can only go in one stall. So I'll just draw the cow as a circle. Right? Cows are not sphericals. So I mean, if you were a physicist, then you would say that, okay, cow is you would consider a spherical cow in vacuum, right? But we are not physicists over here. So let us just consider this cow in this particular stall. Right, so I can put this stall in many, I can put this cow in stall in many different ways. If I have 3 cows and I have 5 stalls, if I have 5 stalls and I have 3 cows, then very quickly, can someone tell me what is the total number of ways I can put them? What is the total number of ways I can take 3 cows and put them in 5 stalls? Well, that will simply be 5 choose 3. Right? I have to choose 3 stalls out of 5 stalls to put the cows in. And oops. So let us go back. Sorry about that. Right? And if the cows are distinguishable, then I will also have a 3 factorial factor coming. Right? That depends on whether the cows are distinguishable or not. Right? Perfect. So suppose I put the first cow over here in this stall. I put the second cow over here in this stall, and I put the third cow over here in this stall. Right? Now the cows are aggressive; they want to fight with each other. Right? So we want to maximize. The distance between the cows. Right? Now, but there are multiple differences, right? So there's one distance between this cow and this cow. And there is one distance between this cow and this cow. So which distance are we trying to minimize? We are trying to maximize the minimum distance. The minimum distance between any 2 cows. Right? So let us suppose that this distance is 6 and this, so let us not suppose that this is 6. Let us just calculate. So this is at 2 meters and this is at 7 meters. So this distance will be 5 meters. Right? Similarly, this is at 7 meters, this is at 8 meters. So this distance is 1 meter. Right? Now the minimum distance among these two is 1 meter out of 5, and 1 is minimum. So we are saying that this is the minimum distance between 2 cows in this particular arrangement. We want to maximize this distance. We want to place the cows as far apart as possible. All right. And this distance, mind you, this distance is not in terms of the stall number. This distance is in terms of the location of the stall. Right, so we have 2 things over here. We have the 0th, 1st, 2nd, 3rd, 4th stall. We have the stall number. That is not what we're talking about. We're talking about the distance in terms of the location of the stall. Is the question clear? Yes. So very quickly, what do you think should the answer for this particular case be? Suppose that this is the arrangement. I have stalls at 0 meters, 2 meters, 5 meters, 7 meters, and 8 meters. And I have 3 cows. Then where should I put these cows? Where should I ideally put these cows to maximize the distance? Yes, the first cow should go in this particular stall. All right. Then I can put the second cow in this stall, and I can put the third cow in this stall. Is that clear? Yes. So this will be the ideal case. And what will be the final distance? The distance will be, so the distance between these 2 cows happens to be 5 meters. The distance between these 2 cows happens to be 3 meters. Right? And the minimum of those distances is 3 meters. So we are making sure that the cows are 3 meters apart from each other. Any pair of cows is 3 meters apart from each other. All right? Perfect. So now the question is that given you have been given N, you have been given C, and you have been given the location of these N stalls. Right? And you have to tell me what minimum distance can you achieve by placing the cows as far apart as possible in the different stalls. I hope the question is clear. So basically, if this is the input, you have to give me the output 3 meters. Right? You have to give me the output 3. All right. Now, how will we do this? How can we do this? So once again, let us start with a very brute force approach. The brute force approach would be to try all possible arrangements of the cows. Right? Try all possible arrangements. So as we just saw, so are the cows distinguishable in this particular case? Does it really matter what the first cow, second cow, and third cow is? No, it does not, right? All that matters is what stalls they are in. So over here, how many possibilities do we have? We have 5C3 possibilities, right? Or basically, we have n choose C possibilities, where n is the number of stalls and C is the number of cows. So if we do this brute force, we will check each of the possibilities, and then for each possibility, we will find the minimum distance. Right? We will find the minimum distance. So what will be the overall time complexity of this brute force approach? It will be order of n choose C times. So once we have chosen an arrangement, we still have to calculate. So let us say that we have several stalls and we have chosen to put one cow here, and one cow here. That is not done, right? We still have to measure these distances and find the minimum distance between any pair of cows. So that will take us an additional of order of n time, because we have to go through every pair of cows, right? The total of time complexity will be n choose C times n. Well, how big is n choose C? Can someone tell me how big n choose C is in terms of O(n) complexity? So what polynomial, n to the power what will it approximately be? This is the same as n to the power C, right? N choose C is the same order as n to the power C. Yes, no? Yes, no? Well, not really. Not really, because binomials flip. From the midpoint, the binomials flip. Right? So we are assuming, so this is if C is less than n by 2. Right? C is less than n by 2. So we can rewrite this as, so let us not write this complex expression. Let us just keep this as n choose C times n. And this is in the worst case. In the worst case, this is equal to order of n to the power C times n. Right? Now, if C is very big, if the number of cows is very big, this complexity is perhaps not that big. Right? If there are 10 cows, then you will have to spend n to the power 10 times. That is very, very bad. Right? So let us try to optimize this approach further. Let us try to optimize this. Okay. So those of you who are familiar with dynamic programming, what would you try to do over here? What would you try to do over here? So anyone who is familiar with dynamic programming would say this, that all right, I have several stalls and I have some cows. Right? I have several stalls and I have some cows. That is simple, right? For every stall, I have to make a yes/no decision. I have to make a yes/no decision whether to put this cow in there or whether to not put this cow in there. Right? So people would try to apply DP over here and say that, okay, for the first stall, I can choose whether I'm going to put the cow in or I'm not going to put the cow in. Again, for the second stall, I'm going to choose whether to put the cow in or to not put the cow in. Right? And so on and so forth. I will build my choices. And by DP, I can finally find the answer. Well, that is perfectly valid. Right? That is perfectly valid. And if you do that, your complexity will turn out to be order of n squared, which is not bad, right? Which is definitely better than order of n to the power C times n, right? But we can do better. So the moral of this story is that even if you have come up with a solution, it is still worth checking if the solution can be optimized or not. All right. Now let us dive into the most optimized approach, which will be using binary search. Binary search. Perfect. So if we are supposed to use binary search, we have to have a search space. We basically have to decide what we are searching for. What are we really searching for over here? Right? Can we search for the location of stalls? That doesn't really make sense, right? Because we have to consider multiple stalls and there are multiple cows. So how it doesn't really make sense to search for the location of a particular stall. What we can search for is the answer itself. We can search for the answer itself. Right? So what is the answer over here? The answer is the minimum distance. And we are trying to maximize this particular answer. Minimum distance between any two cows. All right. So now that we have figured out what we have to search over, let us quickly discuss the bounds. Let us quickly discuss how large this search space is. So what is the minimum value for this minimum distance? What is the least possible distance that we can achieve? What is the least possible distance when we can achieve? Well, if every stall, if we are forced to put one cow in every stall, and every stall is 1 meter apart, right? So they're just next to with each other. They're just next to each other. Then the minimum distance will be just 1. Do you agree? Can the minimum distance be 0? Can the minimum distance be 0? Not really, right? Not really. What is the maximum possible distance that we can achieve? What is the maximum possible distance that we can achieve? Well, this is my first stall. Right? This is my 0th stall is at location 0. All right. And let us say my nth stall, my n minus 1th stall, right? Let us say it is at location, let us say L. All right. And I have to place C cows. I have to place C different cows within this distance. So in the worst case, I mean, even in the best case, doesn't matter how the stalls are arranged. Can I achieve, what is the best distance that I can achieve? If all the stalls are equidistant from each other, then I can simply place the cows one in each of them, right? And then basically my distance will be L by C, right? This is the maximum possible distance I can achieve. Can I achieve more than that? Can I possibly get more than that? No, because once I have placed the cows at equidistant locations, if I try to move any cow to the left or right, then the distance between the previous cow or the next cow, this decreases. Right? And we are supposed to consider the minimum distance between any pair of cows. Right? Minimum distance between any pair of cows. So the maximum possible distance that we can achieve possibly is L by C. Right? And what is L over here? L is simply the maximum of the array. Right? So let us consider that these distances are given to us in the array. Right? So this location of the stalls, this has been given to us in array of size n. Right? So this is simply max of A, right? Max of AL for all I. So we now have the bounds. We now know that we are supposed to look for a value in this search space. This search space goes from 1 all the way till max of A of I. All right. Now, what else is required for a binary search? So now that I have a low and a high, I will calculate a mid, and this mid is going to be my guess. Okay, this mid is going to be my guess. Now I have to check. Several things. I have to check, is the guess perfect? Right? Is the guess valid? And is this the correct answer? That's one thing I have to check. Or I have to check, is the guess too low? Or I have to check, is the guess too high? Right? Because only if I know all these 3 things, only if I know the answer to these 3 things, only then can I adjust my search space. Do we agree? Yes, exactly. We need a proposition. Right? If I don't have these 3 values, I will not be able to figure out in which direction should I move in the search space. All right. So let us quickly look at how we will do that. So suppose that I tell you, you have been given this array A of n, size n, and this is the location of stalls. And I am telling you that, okay, you can achieve a distance of, let us say, 5 meters. Right? We have to verify whether this is true or not. So how will we verify that? How can we verify that? Well, this is very simple. Right? This is very simple. What we can do is, so let us suppose that these are the stalls. Right? And let us suppose that this is at location 0, this is at location 5, this is at location 7, location 11, location 16, location 23. Right? Let us suppose this is how the stalls look. So what we can do is, we can place the first cow in here. Right? We can always place the first cow in the first stall. Then we can move on to the next stall and we can check what is the current distance. Is that distance greater than or equal to 5? Yes, it is, right? So we can safely place the next cow over here because we are trying to achieve a distance of at least 5. We're trying to achieve a distance of at least 5. All right, then we can move on. So when we want to put the third cow, we will come to the next stall and check. Is the distance from the previous cow greater than or equal to 5? So is 7 minus 5 greater than or equal to 5? No, it is not. Right? So we cannot, if we have placed the cow in this stall and we are trying to achieve a distance of 5 meters, then we cannot put the next cow in this stall. All right. What about the next stall? Well, the distance from 5 till 11 is 6. So we can safely place the next cow over here. Does that make sense? Moving on, so we can definitely place the next cow over here. And we can also place the next cow over here. Right? So we can place the cows in this particular manner. Now, if we are able to place all the cows, successfully, right? So remember that we have C cows. Right? If we are able to place all the C cows successfully, then what can we say about this particular guess? What can we say about this particular guess? Is this the correct guess? Not necessarily. Right? This is a valid guess. This is a valid guess. But we are supposed to maximize this guess. Right? So this is a valid guess, but this might not be the maximum value. So we have to continue searching. We have to continue searching with larger values. Right? We have to continue searching with larger values. Suppose that we were not, so if we were able to place it, then we have a valid distance, but the distance can be higher. All right. What is the other possibility? The other possibility is we were not able to place all the cows. Right? For example, suppose over here, let us suppose that my guess distance was, so let me just erase this. So let us say that my guess was that, okay, I can achieve a distance of 10 meters, right? And let us suppose that I had 3 cows to put. So I will try to put the first cow in this first stall. Then I cannot put the second cow in the second stall or in the third stall. I will have to put the second cow over here. Right? I will have to, in this case it will work. So let us just say that we had 4 cows. Let us say that we had 4 cows. So I will put the second cow in this stall. Then I can't put the third cow here. I can put the third cow here. So I will put the third cow over here. Now where do I put this fourth cow? I cannot possibly put the fourth cow because I have exhausted all my stalls. Right? So in this case, we see that we had a guess of 10 meters distance and we tried to place the 4 cows, but we were not able to place all the 4 cows. We were only able to place 3 cows. So that means that my guess is incorrect. Right? That means that my guess is incorrect. Is there anything else that I know? I know that my guess is too high. Right? If 10 meters did not work, then 12 meters or 20 meters or 50 meters will also not work. Right? My guess is too high. I have to reduce my guess. Does that make sense, guys? Yes? So what we are essentially doing is, we are saying that let us initialize the low as 1, the high as L by C. So this is maximum of A of I. Right? So maximum of A of A is just the last location. The location of the last one, A of A dot length or n minus 1, A of n minus 1 by the number of cows, C. Then while our low is less than equal to high, right, what we will do is we will calculate a mid. So our guess is the mid, which is simply low plus high minus low by 2. Do you agree? Now we have to verify the guess. Right? So if works, right, if this array for this number of cows, for this value, for this guess, if this works, so we will write this function works. But if this works, then what can we say? If this particular thing works, then what can we say? We can say that, hey, this guess is valid, but it might be too low. Right? This guess is valid, but we could do better. Right? So we have to increase our guess. Right? How will we increase our guess? We will say low equals to mid plus 1. Right? But this guess worked. Right? This guess worked, so we must also save it. This was the largest guess that worked. So let me also save a variable over here, largest working guess. Right? Let me save a variable over here, largest working guess. And this was initialized with, let's say, 0 or minus infinity, whatever you want. And I can say over here that largest working guess equals to maximum of my guess, my mid So it is maximum of mid, the current guess, comma the largest working guess. All right, I can make sure that whenever I have a valid guess, I save the largest of those valid guesses. Is that clear? On the other hand, if this does not work, then I have to adjust my high. High equals to mid minus 1, right? And at the end of this loop, when this loop is through, I can simply return whatever maximum guess I have found so far. So largest working guess. Does that make sense, guys? Does this binary search make sense? Yes? We still have to write this function, right? We still have to write this works function. Well, this function is very simple, as we saw. How will this function work? So we have to write works. This will take an array. This will take the number of cows. This will take the number of cows, and it will take a guess. So what will we do? We will start from the location first, right? We will say that the previous stall equals to 0, right? We will place the first cow at location 0. Now, how many cows do we have to place now? So for I goes from 1 till c minus 1. Right? We have already placed the 0th cow. Now we have c minus 1 cows remaining to place. Right? So we will go over each cow, and then what will we do? Right? We will try to place the cow in the next stall. So we will also let me also save a stall number over here. Right? So stall number is 1. Right? I have already used up the stall number 0. So the current stall number is 1. Okay. So now what can I do is I can try to put the cow in over there. So I can say while the location of the current stall, right? While a of stall minus a of previous stall. Right? If this distance, while this distance is less than my guess, I cannot really put this cow in the current stall. Right? So I must move on to the next stall plus plus. Do you guys agree? While this is true, I will do stall plus plus. Right? And finally, I will say that, all right, once I have this, I will say previous stall equals to stall. Right? So I will put the cow in there. So this is my loop. Now, of course, this loop might not always work. Right? Basically, when will it fail? When my stall number has become equal to the size of the array. When I have reached the last stall, but my cows have still not been finished. Right? So I can put a condition over here. I can very quickly check over here. So instead of directly doing this stall plus plus, let me do a stall plus plus. And now I can check if stall equals to n. If I have already reached the last stall, then I can return false. Because this guess did not work. I still have some cows to place, but I have exhausted my stalls. Right? So I will return false that, hey, this guess does not work. If I can complete this for loop, that means that I was able to place all the c different cows. Right? I was able to successfully place all the c different cows at a minimum distance of guess. So over here, I can return true. Does that make sense? Does this works function make sense? Yes? Do you guys agree? Perfect. So what will be the time complexity of this? What will be the time complexity of this entire code? Well, let us take it step by step. Right? How much time does the works function take? Given a particular guess, how much time does it take to verify that guess? Well, we have to linearly search through the array of stalls. Right? We have to linearly check the array of stalls. So this works takes order of n time, right? Where n is the number of stalls. Do you agree? Do you guys agree? So, okay, some people will over here say that, okay, you have a while loop. You have a while loop over here, and you have a loop that goes c times over here. So isn't the complexity going to be c times n? Shouldn't the complexity be c times n? Well, no, right? The complexity of this entire for loop is not c times n, because as we see, this variable stall is strictly increasing. Right? This variable stall is never reset. So it can only increase. And the maximum possible value of stall can be up to n. Right? So it is the complexity of this entire nested loop. It is not C times n. It is simply order of n. Is that clear? Yes, perfect. What about this? What about this binary search? So I think I deleted something from here. Right? What about this binary search? So this binary search takes us how much time? It takes us log of the size of search space. What is the size of search space over here? Is the size of search space n? No. The size of search space is this value over here. Right? This is the size of search space. A of n minus 1 by c. Right? This is the size of search space. So this will be the number. This will be the number of times we will have to do the binary search, and each binary search will take us order of n time. So we can say that the complexity of this is order of log of max of ai, max of ai, so the maximum stall location divided by the number of cows, right? The log of that times n. Is that clear? Yes? Yes or no? Well, C over here. Is that clear, guys? So C is not a constant, so we can't really ignore it. So this will be the final value. This will be the final value. And is this better than? Is this better than n square? So do you guys think that this is better than n square? Well, that will depend. That will depend on how large this A of I is. Right? How large this A of I is. Is that clear? So it might be the case that A of I is 1 trillion. If A of I is a very, very large number, then it might make sense. It might make sense to do this n square solution. But that is going to be extremely, extremely rare. Right? So if n is large, then definitely this log value will be much, much smaller. Right? So in general, this approach will work faster. Is it clear? So we saw the brute force approach for this. Right? That was order of n to the power c plus 1. Right? Then we saw the DP approach for this. We did not discuss this in detail. We will discuss this maybe later. So this was order of n square. And then we discussed the binary search approach. And this turned out to be order of log of max of A by C times n. Is that clear? Yes? Any doubts on this particular question? I hope that you will be able to code it. So this is part of the assignments. So please try and code it. You will actually learn a lot when you implement these solutions. Right? And one more thing, please try to make sure that you make the code modular. Right? So just like we have discussed in the class, please define a separate function, right, that will check the guess. You can also write this. You can also write this code over here as well. Right? You can also write this code over here as well. But please do not do that, right? Because then your logic will not be clear. You will be mixing the logic of your binary search with the logic of your checking a guess. Let us keep those two logics separate. Binary search is separate. Checking if a particular guess works or not, that is separate. So please let us do the separation of concerns thing and then keep them in different functions. All right. So let us move on to another question. So this is again fairly challenging question, and this is also a very, very interesting question. Okay. So the question goes something like this: that you have been given an n. You have been given a number n, and this n is a 64-bit number, 64-bit integer, and let us say it is also positive. All right. Let us say it is also positive. Let us also say that n is greater than 2. All right. Let us also say that n is greater than 2. So basically, what values can n take? So n can take a value from, let us say, suppose 3 all the way to 10 to the power 18, perhaps. Right? N can take all these different values. Cool. So now what we are saying is, let us suppose that n written in some base k. N written in some base k. So k can be either 2, in which case we are writing n as a binary number, right? Or k can be ternary, or k can be 3, or k can be 8, in which case we are writing n as an octal number, right? But if we write k in, if we have n in some base k, and if this equals to 1 1 1 1 1 dot dot dot, right? If this is just a string of ones, right? Then we will say that okay, this k is a good base. Good base. All right? Is that clear? For example, let us say that n equals to 7. All right, n equals to 7. Then what different bases will work? What all different bases can work? So first of all, this k equals to 1 will always work. Right? Yes or no? I can always write something in base 1. Right? A number n in base 1 is just 1 1 1 1 1 n times. Do you guys agree? Yes? Let us not do that. Let us ignore this k equals to 1 thing. All right? Let us ignore this k equals to 1 thing. So we are also considering that k is greater than 1. That k is greater than 1. Okay. Now let us try some other base. So 7 written in base 2. What does this look like? What does 7 in base 2 look like? 7 in base 2 is, so this is base 10, my bad. This is base 10. In base 2, if I write it, then it will be 1 1 1. Right? So 2 is a good base. 2 is a good base for 7. All right? Are there any other good bases? Are there any other good bases? Yes, no? Well, what happens if we write 7 in base? What happens if we write 7 in base 3? What do we get? So we get 1, then 4 remains, right? Then we will get, so just give me a second. So the last, so 7 is basically equal to 3 to the power 0 plus 3 to the power 1 plus 3 to the power 2. So this is going to be 3 to the power 3. Yes, so this is going to be 2 times 3 to the power 1 plus 1 times 3 to the power 0. Yes, so this is 7. This is 7. So what will 7 look like in base 3? What will 7 look like in base 3? 7 will look like 2 1 in base 3. Right? 7 is 2 1 in base 3. So is this a string of ones? Is this a string of ones? No, this is not a string of ones. So 3 is not a good base. Excuse me. 3 is not a good base. All right, let us continue. So we can check the base 4, we can check the base 5. That is also not going to work. There is some other base that is going to work. Right? 7 in base 7 is also equal to, in base 6, this is going to be equal to 1 1. Right? In base 6, this is also going to be equal to 1 1. Do you guys agree? Yes. In fact, if I have any n in base 10, then this is equal to 1 1 in base n minus 1. Yes or no? 1 1 in base n minus 1, that is simply n. Why is that? Because see, 1 1 in base n minus 1, this is equal to n minus 1 to the power 0 times 1 plus n minus 1 to the power 1 times 1. Right? And that is equal to what? N minus 1 plus 1, which is just n. Right? So any number n that I have, I can always write in one less base and get a string of ones. So 7 equals to 1 1 in base 6. Right? 13 equals to 1 1 in base 12, and so on. Do you guys agree? So n minus 1 is always a good base. Right? N minus 1 is always a valid base. So this is also a good base. Right? Cool. Now the question once again is that you have been given a value of n, right, such that n is greater than equal to 3 and n is less than or equal to 10 to the power 18, suppose. So it is a 64-bit integer, positive integer. We have to find the smallest good base. All right, so we found several different good bases, right? For 7, we found that 2 works. So we found that 2 works, 3 does not work, 4 does not work, 5 does not work, 6 works. Right? That is what we found for 7. So what will be the smallest good base for 7? what will be the smallest good base for 7? It will be 2. Right? It will be 2. So smallest good base. So for example, if n equals to 7, then the answer will be 2. And why 2? Why not 1? Because 1 works for everything. Right? If we allow 1, then for every number the answer will just be 1. Because base 1 works for everything. Is that clear? So we are saying that the smallest good base, let us call this k, is greater than or equal to 2. So this is the question. I hope the question is clear. Given an integer n, return the smallest good base. For example, if your value is 7, then you're supposed to return the value 2. All right. So what can our approach be over here? What can our approach be over here? Let us start with the most brute force approach. Brute force approach. What will the brute force approach look like? In the brute force approach, we can simply check all the possible options. Right? We can simply check all the possible options. So we can go from base k equals to 2 all the way till n minus 1. Right? We can check all these different values. Now, once we have a base, we have to convert n into that base, right? Base k, and check if this is a string of ones. If this is a string of ones, well, how much time does it take to convert a number into base k? How much time does it take to convert a number into base k? Can someone quickly tell me that? It will take me log of n time base k. It will take me log n time with a base k. This is how much time it will take me to convert a number. Why? Because I have to repeatedly divide that number by k. Right? I will say that, okay, the last digit equals to n mod k. Then I will divide the number. Right? I will say n by equals to k. N by equals to k. This is not or this is a simple division. Right? Then I will say d1 equals to once again n mod k. And then I will again say n equals to n by k. Right? And this will be in a loop. This will basically be in a loop. That is how I convert the base. So it will take me log of n time base k. All right. So what is the total time complexity over here? I have these many bases to check. And it takes this much time to check each base. So it will be order of n times log n. Right. So my brute force approach takes me order of n times log n time. Is that clear? Yes. Now this is not very good, right? This is not very good. If my n is, let us say, 10 to the power 18, then it will take me 10 to the power 18 steps. That is definitely not possible. I cannot do 10 to the power 18 steps on any computer. Yes. So we should better come up with a faster solution. We should try to come up with a faster solution. Okay. So what can we do over here? What is the first thing that comes to your mind? What is the first thing that comes to your mind? The first thing, since we have been doing binary search, might be that, okay, let me make a guess. Let me guess base B. Let me guess base B and check if the guess is valid or not. Yes, that is what comes to your mind. That let us take a base B, let us consider a random base B, and let us check if it is valid or not. Well, this is not going to work for this case. This is not going to work for this case. Why? Suppose that my number was 7. I checked the base 2. And it worked. What does that tell me? Does that really tell me anything? That tells me that 2 works. But that is not enough, right? I also have to understand, is my guess too low or is my guess too high? Yes. Just because 2 works, that does not mean that my guess is too low or that my guess is too high. Do you agree? It might be the case that 7 of 6 still works, right? So for the base 7, 7 of 2 works, 7 of 3 does not work, 7 of 4 does not work, 7 of 5 does not work, 7 of 6 works. This works. So suppose you make a guess. There is a valid value to the right of it as well as to the left of it. And you do not know in which direction you have to go. So if it turns out to be false, if you figure out that, okay, the guess did not work. So are you supposed to increase the base or are you supposed to decrease the base? Are you supposed to increase the low or are you supposed to decrease the high? Does that make sense? We have no way of knowing in which direction should we move our guess. So we cannot do the binary search over base. Does that make sense? Because once again, if we go back to the first class, if this is our search space, then we need to come up with a proposition such that all the answers here are yeses and all the answers here are no's, so that we can search binary search for this midpoint. For this particular thing, the answer over here is yes, the answer over here is yes, the answer over here is yes, but all the other numbers can be no. Right? We don't really know. It can be randomly. It can be in a random manner. So binary search is not going to work for this proposition. Is that clear? Yes. It seems very, very seductive to try to apply binary search over here. I have a base. I can verify if it is a valid base or not. So let me just binary search over the base. That is not going to work, unfortunately. So what else can we do? What else can we do? So we have to look at the question from a different perspective over here. We have to look at the question from a different perspective over here. So let us suppose that we are talking in base B. Right? Suppose we are talking about in base K. Suppose base K. Right? Then, if basically my number n in base K is a string of ones, I already know what the string of ones is, right? I can construct this string of ones, right? I know that this is in base K. I know that this is a string of ones. The only thing I don't know is how many ones there are over here. Yes, how many ones there are over here. Let us call this value I. Does that make sense? So n written in base 2 will have 3 ones. Right? N written in base 6 will have 2 ones. Right? So instead of trying to binary search over the value of k, let me try to binary search over the value of I. Okay, let me try to binary search over the value of I. But let me first establish a relation between these two. Let me first establish a relation between these two. So if n in base k is a string of ones in base k, so n is equal to a string of ones in base k, right? And let us say that there are I ones over here. Then what can I say? Is there any relationship between n and k? Is there any relationship between n and k? Yes, there is, right? What is the relationship? I know that 1 times k to the power 0 plus 1 times k to the power 1 plus 1 times k to the power 2 plus all the way till 1 times k to the power I, right? This thing equals to n. Right? If I have this number in base k, then this is the expansion of it, and I know that this must be equal to n. Right? What can I say? N equals to summation of k to the power I, or k to the power, let's say, x, for x equals to 0 till I. Right? So this is what is this? This is a geometric progression. This is a GP. So can I write the sum of it? The sum of it is simply k to the power I plus 1 minus 1 by what? By k minus 1. Right? So the sum of a GP, summation of r to the power I, for I equals to 0 till k, this is equal to what? 0 till n. This is equal to r to the power n plus 1 minus r to the power 0 by r minus 1. Right? Yes. So just notice that there is this denominator over here. Right? You can't simply say that the denominator is 1. Right, Shazia? So Shazia, there's a small mistake in your formula. You have to make sure that this denominator is also dependent on k. Right? So we can say that n equals to k to the power I plus 1 minus 1 by k minus 1. This is the relation that we have established between n, k, and I. Now I know that I cannot really binary search over k, but that's okay. Let me binary search over I. Right? Let me binary search over the value of I. All right. Now let us suppose that I have I ones over here. Right? Let us say that I have I ones over here. Right? And this is equal to n. Right? This is equal to n. Then what if I'm trying to minimize? So remember that I have to find the smallest good base. Right? I'm trying to minimize the value of k. So what am I trying to do with the value of I? If see n is my constant. Right? N is my constant. I'm trying to minimize the value of k. So what am I doing with I? I'm trying to maximize the value of I. Right? I'm trying to maximize the value of I. Do you agree? Yes or no? Right? Yes or no, guys? So that is one thing we know. Perfect. We know that we are trying to maximize the value of I. All right. Let us also consider what is the search space of I. Search space of I. What is the search space of I? So so this can be, so let us suppose that I write n in base 2, right? This is the smallest base that I can possibly have. So that will give me the largest possible string of ones. Largest possible string of ones. How many ones will I get when I write n in base 2? I know that n is a 64-bit integer. 64-bit integer, right? So the maximum search space, the maximum value of I can be 64. Right? So I can have all the way from 2 all the way to 64 ones in my string. All right. Now, once again, the problem over here arises. If I know that this sequence of I works, does that tell me anything about this sequence of I or about this sequence of I? Does that tell me anything about this sequence of I or this sequence of I? It does not. Right? I know that I have to maximize the number of ones. But if this works or if this does not work, it doesn't tell me whether I should increase it or decrease it. So I cannot really binary search. Over the value of I either. That's sad. But how many i's can there be? We just established that the maximum possible value of I can be 64. On the other hand, when we were talking about k, we established that the maximum possible value of k can be up to n minus 1. So what would we rather search over? Should we search over k or should we search over I? This can be up till n minus 1. This can only be up till 64. Right? So this is much better, right? Do you guys agree? Searching over I is much better. So I can simply check for every possible I. For I goes from 2 till 64. Let me check for all the possible strings of 1. Right? Let me check all the possible strings of 1. Now what I will check? Now I will see whether n can be written in the form of 1 1 1 1 1 I ones to the base k. Whether I will try to see whether any such base k exists that will give me this. Does that make sense? I can go over every I. Yes, but how do I find this k now? How do I find this k? I know the relationship between these two, right? I know the relationship between all these numbers. I know that n equals to k to the power I plus 1, right? N equals to k to the power I plus 1 minus 1 by k minus 1. I know this relationship. So now, if I have the value of I and if I have the value of n, can I find the value of k? Can I find the value of k? Yes. How will I find the value of k? That is difficult, right? I will have to manipulate the formula. Right? If I want to find the value of k, I will have to manipulate the formula. I will have to extract k out of it. So can someone solve this equation for me very quickly? Well, you can't really do that, right? Because this I might be a very, very large number. Right? And you don't, so for higher degree polynomials, you don't always have a way of solving an equation. So you can always solve a quadratic. If you have a quadratic equation, you can always solve it. If you have a cubic equation, you can always solve it. Right? But for higher equations, I'm not sure for the fourth power, but I know that from fifth power and above, right, it is not always solvable. It is not always possible to solve a higher degree polynomial. All right. So this equation might not be solvable. So what can we do? Do we have to give up? No. Here is where we can binary search. We can binary search for the value of k. Right? We can try to plug in the value of k and try to binary search for an answer that works. Is that clear? So what we will do now is we now have to find a k that works. What is the maximum possible value of k? The maximum possible value of k, so the minimum possible value of k is 2. The high maximum possible value is n minus 1. And now I can binary search over this value of k. I just have to find one k that works. I can binary search for k which satisfies this equation. which satisfies the equation n equals to k to the power I plus 1 minus 1 by k minus 1. Is that clear? So just like in the first class, we tried to binary search. So we did not do it in the class, but it was part of your assignment. Right? So in the assignment, you had to do a binary search for the square root of a particular number. Right? For the square root of a particular number. Yes, so n minus 1. Right? This is n minus 1. Right? So we can binary search over the value of k. Is that clear? So how much time will this binary search take? How much time will the binary search for k take? This is my search space. Right? This is my search space. My search space has size of n. And I'm doing a binary search, so it will take me log n time. Log n time to binary search for a value of k. But I have to do this 64 times. I have to do this for all values of I. So this will be times 64. So the overall time complexity of my approach will just be 64 times log base 2 of n, which will just be log n. That is amazing. Right? We went from an n log n solution. We went from an n log n. What happened over here? N log n brute force, and we reduced it down to a constant times log n. Is that clear? Yes. So even though the question does not directly involve binary search, there is still an involvement of binary search. And the moral of this particular question is that be very, very careful. Be very, very careful. For binary search, you just don't have to make and verify a guess. You also have to understand, given the guess, if that guess worked, then is the guess too high or too low? Right? If the guess worked or if it did not work, this is not enough. You also have to establish, is the guess too high or too low? Because if you cannot do that, then you will not be able to binary search for your answer. Is that clear? Perfect. Ankush has asked a very good question. Ankush is saying, how can we know whether binary search will be applicable for this particular question? Now, that is a very, very tricky question. So basically, the most common answer you will find to this is practice. Right? The most common answer that you will find to it is that, okay, if you just practice, then practice will make you perfect. You will get to know which way, which approach you have to apply. But that is not the entire truth. There is a separate way as well. So there's a systematic way. There is a systematic way of approaching problems. Right? Now, unfortunately, I cannot teach this systematic way in a YouTube class. Right? It cannot be taught in a 1-hour class. So the entire scalar curriculum, the entire scalar curriculum of DSM algorithms is based on, I'm trying to teach you this systematic way. Right? So that whenever you get a new problem, you can just apply the systematic algorithm and try to come up with a solution for that. Okay, that is what we teach in the scalar classes. All right. So, I mean, we could cover this, but this is going to take a very, very long time. We will have to take a very long class. We'll have to consider all the DS algo things, and then we will have to tell you the approach. Perfect. So that is it for today's class. Let us end the lecture now and see you in tomorrow's class. All right. So tomorrow's class is going to be on hashing, and see you then. So once again, you can find the assignment set in the video description. Please make sure that you attempt the problem set. Okay then. Bye bye. Have a nice day, guys. See you tomorrow.